Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. You're given 4 numbers: 4, 5, 6, 7. Add, subtract, multiply, divide them in any order. Make exactly 24. That's the game of 24. Earlier this year, researchers gave this puzzle to an AI using chain of thought prompting, and the model solved just 4%. Then they tried something new. Same model, same puzzles. Success jumped to 74%. That technique is tree of thoughts. It doesn't think in a straight line. It explores multiple possibilities, evaluates them, and backtracks when it hits a dead end. This is part 4 of our Prompt Engineering Masterclass. If Chain of Thought was a scratch pad, Tree of Thoughts is a full strategy board. By the end of this video, you'll know exactly how it works, and when using it will wreck your token budget. In the next few minutes, you'll walk away with 3 things. First, exactly why Chain of Thought's single-track mind fails on real, messy problems. Second, the step-by-step mechanics of Tree of Thoughts, how it generates multiple branches, scores them, and prunes dead ends. And third, the ugly truth about token costs, when Tree of Thoughts earns its keep and when it's a budget disaster. Quick recap from Part 3. Chain of Thought works by forcing the model to write down intermediate reasoning steps before spitting out the final answer. Input becomes Thought 1, then Thought 2, then Final Answer. It turns a black box into a transparent sequence and boosts performance on math and logic. But notice, that line is one way. No forks, no second chances. Once a thought is committed, the model can't go back and try a different path. That's fine when the solution path is unambiguous, but it's catastrophic when the first guess is wrong. Picture a mini crossword puzzle. You're filling a 5x5 grid. You confidently place a 5-letter word across the top row. It fits the clue perfectly. 3 minutes later, that word blocks every possible vertical answer. The puzzle is now unsolvable unless you erase that first word and start over. Chain of Thought doesn't have an eraser. It commits to the first plausible step and marches forward, even if that step later creates a contradiction. That's the core motivation behind Tree of Thoughts. Letting the model explore several first moves, evaluate how well each one works, and backtrack the moment a choice hits a dead end. Side by side, the difference is stark. Chain of Thought is a single-minded march down one road. No turning back, no second opinions. Tree of Thoughts opens a branching tree of possible next steps at every decision point. It generates multiple candidates, scores each one on its promise, and only pursues the best leads. When a branch turns out to be a dead end, it backtracks and tries another. This isn't a minor tweak. It fundamentally changes how the model approaches a problem. Let's step back for a moment. Why does Tree of Thoughts work so much better than Chain of Thought on difficult problems? Because every branch represents a different hypothesis. Imagine you're troubleshooting an Azure application that's suddenly unavailable. One engineer immediately blames the network. Another suspects DNS. A third thinks it's an expired certificate. A fourth investigates authentication. If everyone follows only the first idea, they may spend hours chasing the wrong problem. Instead, Experienced teams quickly explore several possible causes, eliminate the impossible ones, and focus on the most promising path. Tree of Thoughts applies the same strategy. Instead of assuming the first idea is correct, it generates several possible next steps, evaluates each one, and continues exploring only the strongest candidates. It's less like guessing, and much more like systematic problem solving. Let's lock in that core concept. Quick checkpoint. Chain of thought can only follow a single reasoning chain with no backtracking. What fundamental change does Tree of Thoughts introduce? Let's make that concrete. The root is the problem you're trying to solve. Say, the game of 24. The first level shows candidate thoughts, each a possible next step. Maybe 7 plus 5 equals 12, or 6 minus 4 is 2. The model gives each a confidence score, 90%, 70%, 30%. It then goes deeper on the highest scoring branch. In this diagram, the 90% thought spawns a follow-up step scored 85%. A thought isn't just a token, it's a coherent language sequence that represents a meaningful chunk of reasoning. This tree structure gives Tree of Thoughts its name. Let's lock that in. Quick check. What's the single biggest limitation of Chain of Thought that Tree of Thoughts fixes? The answer: Chain of Thought can only walk a single path forward. It can't generate multiple hypotheses, compare them, or backtrack when an earlier step turns out to be a mistake. Tree of Thought solves that by building a branching tree with self-evaluation. You don't need a complex orchestration framework to start. The generation step is as simple as this prompt. Given the current state, propose 3 possible next steps to solve this puzzle. Output them as a numbered list. That one instruction forces the language model to produce multiple divergent moves instead of a single continuation. You've just created your first branching point. The model will respond with 3 candidate actions, just like the 3 experts brainstorming their first ideas. Once you have a handful of thoughts, the next step is evaluation. The model scores each candidate, and you keep only the best ones. Here we see candidate A with around 90% confidence, candidate B around 70, and candidate C down at 30. That last one gets pruned immediately. DFS starts by pursuing the most confident branch, like a treasure hunter spotting a shiny artifact down the left tunnel. It descends into that thought, generating sub-thoughts until it hits a dead end. No valid move left. Then it retraces its steps, climbs back up to the last junction, and tries the next unexplored branch. This is exactly how Tree of Thought solved the 24 puzzle. It didn't give up when the first arithmetic path failed. It simply walked back up the tree, picked a different operation, and kept digging. Tree of Thoughts needs a strategy for deciding which branch to explore next. The 2 most common approaches are breadth-first search and depth-first search. Breadth-first search explores every option at the current level before moving deeper. Imagine searching every room on the first floor of a building before going upstairs. It's thorough and reduces the chance of missing a good path. But it's also expensive because it evaluates many possibilities. Depth. First search takes the opposite approach. It follows the single most promising path as far as possible. Only when that path fails does it backtrack and try another. Think of exploring one hallway until you hit a locked door, then walking back to the previous intersection. DFS is usually much faster and cheaper. That's why many practical Tree of Thoughts implementations prefer it. The trade-off is simple. Breadth first. Search buys confidence. Depth first search buys efficiency. There's actually a third strategy that's very popular in production AI systems. It's called beam search. Instead of exploring every branch like breadth-first search, or only one branch like depth-first search, beam search keeps only the best few branches at every level. Imagine interviewing 100 job candidates. Breadth-first search keeps evaluating all 100. Depth-first search hires the first promising person immediately. Beam search narrows the field to the 5 strongest candidates and continues evaluating only them. This approach dramatically reduces cost while still preserving multiple good options. Many enterprise AI systems use beam search because it offers an excellent balance between accuracy and efficiency. Quick mental check. You've seen ToT's one-track mind. Now, when DFS leads the model down a promising branch that ends in a contradiction, what does it do? Pause and think. Then the answer appears. Those upcoming accuracy numbers, the leap from around 4% with chain of thought to over 70% with tree of thoughts, often, come straight from the original Tree of Thoughts paper's game of 24 experiments. Here's the scoreboard that shocked the research community. On a 100 game of 24 puzzles, same model, same day, Chain of Thought solved only 4% correctly. Tree of Thoughts, 74%. That's not a bump, that's a transformation. Here's a simplified view of the actual search. The model proposed several opening moves. The evaluator gave a sky-high score to 7+5, so DFS dove there, quickly chaining 12-6 and then 6-4. Game over. Meanwhile, a rival branch 7-5 looked plausible, but soon hit a dead end at 29-4 max 25. Because ToT evaluates every step, it recognized the futility and pruned that branch before it wasted more compute. The ability to jettison bad intermediates on the fly is precisely what lifted success from 4% to 74%. This loop captures the entire Tree of Thoughts algorithm in a few lines. First, the model generates several candidate next steps, usually 3 or 4. Then, the LLM acts as its own critic, scoring each candidate's promise. The most confident thought is selected and added to the solution. If that chain later leads to a contradiction, the algorithm pops the dead step off the path and tries the next best option. This generate, evaluate, expand, backtrack cycle repeats until a solution emerges or the whole tree has been explored. Let's zoom out and see where Tree of Thoughts fits inside a real AI application. A user submits a complex request. The planner generates several possible approaches. Each approach becomes a branch in the thought tree. An evaluator scores every branch based on quality, confidence, or business rules. The search algorithm decides which branch to explore next. Once the best reasoning path is complete, the language model generates the final response for the user. Notice something important. The language model isn't doing everything by itself. Tree of Thoughts is really a workflow that coordinates planning, evaluation, search, and generation. That's why you'll often see it inside AI agents and enterprise automation systems rather than standalone chatbots. Here's the part nobody mentions at the keynote. That 74% accuracy didn't come cheap. Tree of Thoughts burns through tokens like a bonfire. While ToT might nibble 200 tokens pondering a puzzle, ToT routinely devours 2,000 to 5,000 per problem. At current API prices, a single puzzle might cost a couple of cents. Harmless, until you scale to thousands of queries in a production chatbot, and suddenly you're looking at a bill that makes your CFO flinch. The real skill in prompt engineering isn't just knowing how to build a thought tree, it's knowing when the cost is worth it. And that's exactly what we're breaking down next. Time to get tactical. Use tree of thoughts when the problem has a large search space and exploring alternatives genuinely pays off. Puzzles, multi-constraint planning, creative generation, where you need the best of several ideas. Skip it for factual lookups, yes, no questions, or simple classification. But here's a cost you can't ignore. Tree of thoughts can consume 10 to 50 times more tokens than chain of thought, depending on branching factor and depth. That's from the Comet article on LLM applications. So before you build a thought tree, ask, is the accuracy gain worth the token bill? If chain of thought already gets the right answer more than 95% of the time, adding a tree is just expensive theater. Save those tokens for the genuinely hard stuff. Time for a quick cost sanity check. You've just seen how token consumption explodes with branching. Pause and answer before the reveal. These techniques often sound similar because both explore multiple reasoning paths. But they're solving different problems. Self-consistency asks the model to solve the same problem several independent times. Afterward, it simply chooses the answer that appears most often. It's like asking 5 students to solve a math problem separately and then taking a vote. Tree of Thoughts works differently. Instead of waiting until the end, it evaluates every important decision while the reasoning is still happening. Weak ideas are eliminated immediately. Promising ideas continue growing into deeper branches. One technique chooses the most popular answer. The other continuously searches for the strongest reasoning path. Understanding that difference will help you decide which technique fits your application. Take the real 5x5 mini crossword from the original Tree of Thoughts paper. The empty grid is the root. First, the model picks a clue, one across. It proposes a few words, evaluates them, and settles on cat with a confidence of 0.9. So far, so good. Then it moves to one down, which shares the first letter. The model suggests car, but car makes a later clue impossible because of letter constraints. That's a dead end. A chain of thought approach would be stuck because it can't undo a committed word. But Tree of Thoughts with depth-first search immediately backtracks, discards car, and explores the next candidate, bat, which fits perfectly and allows the puzzle to continue. Quick recall question. Self-consistency, Tree of Thoughts. Both explore multiple paths, so the confusion is real. Pause and answer before the reveal. Turning an LLM into a critic is one of the simplest yet most powerful moves in Tree of Thoughts. Here's the exact evaluation prompt used in the paper. You give it the current state, maybe a half-filled crossword grid, and one candidate word. Then you ask for a numeric score from 1 to 10 and a justification. That number isn't just window dressing. It's what makes ranking and pruning possible. When you have 3 candidate words, you can sort by score, explore the most promising one first, and throw away the low-confidence options before they burn extra tokens. You don't always need an external loop to do Tree of Thoughts. The 3-expert trick packs the whole pattern into a single API call. You ask the model to roleplay 3 experts who each think independently, share their steps, and leave the discussion the moment they spot an error. This forces the LLM to internally generate multiple branches, evaluate them against each other, and prune on the fly, all inside one response. It's not as rigorous as a full DFS with a separate evaluation model, but for many problems it gives you a huge accuracy boost with zero extra infrastructure. The fastest way to burn your API budget is deploying Tree of Thoughts, where a simple direct answer would have worked fine. Yes or no? Single choice classification? A fact lookup? ToT will happily generate 16 branches, rate them all, and still arrive at the same one-word answer you would have gotten for 100th of the cost. The rule of thumb is brutal but effective. If chain of thought already hits 95% accuracy on a task, do not invest in tree of thoughts. You're paying for exploration you don't need. And when you see the numbers in the next scene, like 15,000 tokens per problem at branching factor 4, that benchmark comes from the Comet analysis of ToT cost scaling. Token consumption doesn't climb, it explodes. With a fixed depth of 4, moving from plain ToT to a branching factor of just 2 already balloons to thousands of tokens. At 4 branches, you're looking at 15,000 tokens per problem. That's why the 10 to 50x multiplier is real, and why you must budget carefully. Quick cost checkpoint. You've seen how fast tokens multiply. Pause and answer before we move on. The evaluator isn't a crystal ball. It can only look one step ahead. Picture this. The model picks a horizontal word that fits every visible letter, and the evaluator awards it a mighty 9 out of 10. Confident, the algorithm commits. 2 steps later, that word blocks a vertical clue. The letter combination makes it impossible to solve. The evaluator didn't see the domino effect coming because it lacks long-range constraint understanding. You end up burning tokens backtracking from dead ends that a little more foresight could have avoided. When you notice this pattern, it's often a sign to tighten your evaluation prompt or add a lightweight look-ahead rule, like checking cross constraints before scoring. One of the cleverest ways to reduce ToT costs without sacrificing accuracy is splitting the workload across 2 models. A smaller, cheaper model, Llama, Haiku, a fine-tuned T5, generates the candidate thoughts. Then a stronger, more expensive model steps in exclusively as the evaluator. The cheap model churns out ideas fast and cheap. The expensive model only has to score them, a much shorter prompt. This division of labor keeps your branching factor high for exploration, but slashes the token cost of the evaluation step, where the expensive model would normally burn the most budget. Let's look at a real enterprise scenario. Suppose an organization wants to migrate 200 on-premises applications to Azure. Should each application be rehosted, refactored, replatformed, or completely replaced? A simple chain-of-thought approach may commit to the first reasonable migration strategy. Tree of Thoughts explores several migration paths for each application. One branch minimizes cost, another minimizes downtime, another prioritizes security, another focuses on long-term maintainability. Each option is evaluated before moving forward. Instead of settling for the first acceptable answer, the AI recommends the strategy that best satisfies the organization's priorities. This is exactly the kind of planning problem where Tree of Thoughts delivers tremendous value. Tree of Thoughts is powerful, but it isn't magic. Every additional branch increases the amount of work the AI must perform. As the search tree grows larger, token usage, latency, and cost all increase. Eventually, the search becomes too expensive to justify. That's why enterprise AI systems rarely search every possible path. Instead, they use heuristics, beam search, business rules, or learned evaluation models to eliminate weak branches as early as possible. The goal isn't finding every possible solution. The goal is finding an excellent solution efficiently. That's an important distinction. Engineering is almost always about optimization, not perfection. Last scenario flagged a huge risk. What if your evaluator gets it wrong? Here's a quick recall to lock in why that happens. When the LLM evaluates a candidate thought, it only sees the current partial solution, it can't fully simulate future constraints. So a word that fits perfectly in one direction of a crossword may make a vertical clue impossible. The evaluator gives a high score, you branch deeper, and only later you hit the wall. Let's see what a Tree of Thoughts-powered coding assistant looks like. Paste a classic LeetCode problem, ToSum, and hit Generate Approaches. The model doesn't just spit out one solution. It branches, dynamic programming, greedy, two-pointer. Click Evaluate, and the LLM scores each branch. Two-pointer gets a 9 out of 10 for efficiency and correctness. Greedy scores A3. It's pruned on the spot. The assistant picks the top node, and we're done. This is ToT in action. Propose multiple paths, self-evaluate, and cull weak branches before committing. Picture this. You give a ToT-powered agent a multi-city trip with a hard $200 budget. The tree route is New York. 3 possible first legs, a direct flight to San Francisco for $300, an overnight flight for $200, or a train to DC then SF for $150. Each branch spawns next step options, flights to London costing $400 or $500. The evaluator tallies total cost. The $300, $500 path hits $300 and gets pruned immediately. The $300, $400 with layover comes in at $700 under budget and survives. The model backtracks from dead branches and ultimately keeps the cheapest valid path. That's Tree of Thoughts as a personal travel agent. Let's finish with 3 practical rules you'll use throughout your AI career. Rule number 1. Use Tree of Thoughts only when multiple solution paths genuinely exist. If the problem has one obvious answer, a simple prompt or chain of thought is usually enough. Rule number 2. Always balance accuracy against cost. Every additional branch consumes more tokens and increases latency. The best solution isn't necessarily the smartest. It's the one that delivers the best business value. Rule number 3. Remember that Tree of Thoughts is only one planning strategy. Modern AI agents often combine Tree of Thoughts with retrieval, tools, function calling, and workflow orchestration. As your AI systems become more advanced, these techniques work together rather than replacing one another. You've just mastered evaluating and backtracking with Tree of Thoughts. Next, you'll combine that same evaluation mindset with real-world actions using React prompting. Before you jump into Part 5, take one concrete step right now. Open your notes and write down one scenario from your work where a branching decision-making process would beat a simple linear instruction. That's the first prompt you'll test when we move to React. If this series is helping you move your career forward, smash that like button, subscribe, and grab the full Prompt Engineering Masterclass playlist. We're building real, hireable skills. No fluff, no gatekeeping. See you in the next one. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.